Okay, so Ward is, I guess, online now. So everybody, welcome Ward to as our speaker this evening. Ward, he does everything. He's really smart, and he's got a lot of things, a lot of books out, grounding and other things. But he's going to talk tonight on End-Fed Halfwave antennas. So Ward, take it away.
Basically, what I'm going to talk about is the End-Fed Halfwave, which has certainly gotten a lot of interest, and a lot of people are using it for portable operations. Some it's on the air, all that kind of thing. But there's a lot of mythology about it. So what I thought I'd do is put together a presentation that discusses the End-Fed Halfwave and what it is all about. Okay, so here we go. The overview is we're going to talk about the End-Fed Halfwave family tree. Where does this antenna come from? It's actually very similar to other antennas that we're much more familiar with, and as a matter of fact, it's identical to them. So it seems to have this interesting name, so people think it's some kind of an odd one-off antenna. It's not. So we're going to talk about where it comes from. And then in-feeding, which is kind of a mysterious thing. It's got a lot of mystique about it. Trying to feed something at the end of a wire, there's some myth versus reality on that. The key to this antenna working properly is the impedance transformer. So then I'm going to jump in and describe what's going on with the impedance transformer and what makes that work. Then we're going to talk about this whole question of counterpoise, which is a very old word in amateur radio antennas and antennas in general. And what is the counterpoise? And on this antenna, do you need one? What does it consist of? Then, after we covered the antenna basics, we're going to go through putting the End-Fed Halfwave to work. How do you make this thing play, install it, build it, and basically use it in your station, whether it's a fixed station or a portable station. And then by the end of the talk, you'll understand what the End-Fed Halfwave is, and you'll feel much more confident in using it, selecting it, building it, putting one up. Okay, so let's keep going here. Let's go back in the family tree to the very root of this antenna, and that is the center-fed half-wave dipole. This is the first antenna ever used. Professor Herr Dr. Hertz used a center-fed half-wave dipole to demonstrate the existence of electromagnetic waves in his experiments in the late 1880s. And you can see a picture of his apparatus there. It had about a 1 meter piece of wire. There's a tiny little spark gap in the middle, a couple of very small marble-sized metal spheres there, and it's held up with standoffs. And then at the end of each end of the wire, you can see a much larger metal sphere about the size of a large grapefruit. And this is a center-fed half-wave dipole. And you can go to Wikipedia and read all about this stuff. Anyway, he was exciting this apparatus here in his lab with sparks and electrical discharges, and he had two of these things, and he could transmit from one to the other, and he would see a little spark appear across the center gap in the middle. And so he was able to reflect the waves and focus the waves and do all this kind of stuff. But it was about a 1 meter long half-wave dipole, so the fundamental wavelength was about 2 meters. So Hertz was our first 2-meter operator. And somebody asked him about what is the use of these things that he discovered, these electromagnetic waves, and he replied, nothing, I guess. So there's your scientist for you. But anyway, a dipole is still the best bang for the buck in ham radio after 130 years. It's a rare ham that hasn't used a dipole at some point on HF, and they just want to work. And it's a good thing because that allowed Dr. Hertz to demonstrate that radio actually existed. So that's the center-fed half-wave dipole. That's the root of the tree. When you talk about a dipole, the dipole is a two-part word with di meaning two and pole refers to voltage polarities, not the two poles you use to hold it up, but voltage polarities. You have one positive voltage, one negative voltage, and so that forces the electrons to flow in the dipole, and then the polarities flip like this, and the current goes the other way. So the current is flowing back and forth in this dipole. When we talk about a resonant dipole, center-fed half wave, it's half wavelength long, it's resonant and the current and the voltage are in phase everywhere along the antenna. Now, in that picture at the bottom, which you can also see in the antenna book and other publications, what you see is a graph of the current, which is that big archy thing, solid line, with the maximum in the middle. And then the voltage is the maximum at the ends. And you can see the two polarities. On the left, you have a positive polarity. On the right, you have a negative polarity. So that positive to negative polarity causes the current to flow along the antenna. Half cycle later, it reverses and the current goes the other way. But that's all that resonant means, is current and voltage are in phase everywhere. And if you think about what impedance means how hard you push to how much you get. It's that ratio. And so how hard you push is voltage and how much you get is the current. So at the middle of the antenna, you have low voltage and high current. So if impedance is the ratio of voltage to current, you have a low impedance at the middle. And that's what makes a center-fed half-wave dipole good for driving with coax, is it's a low impedance and it's suitable for connecting to a piece of coax feed line at 50 or 75 ohms. So that's the secret. That's the center-fed half-wave dipole. It has two voltage polarities that cause the current to flow back and forth along the antenna. It's resonant with current and voltage in phase everywhere. And at the center, it has low voltage and high current. So it has a low feed point impedance. You can use a center-fed dipole on its harmonics, and many of us have done that. For example, use a 40-meter half-wave dipole on 15 meters. Its third harmonic, 7 to 21 megahertz. The dipole is resonant on its harmonics, but it's no longer half-wave, and it's not really a dipole because it has several polarities along the antenna. What we have at the bottom is a drawing of the same half-wave dipole used on its third harmonic. The feed point is still in the center where that little circle is, but now we've extended the antenna on each end one more half wavelength. So now we have 3 half waves because we're on the third harmonic. And there are multiple points along the antenna with low impedance. That's where the current is high and the voltage is low. And you can see that the blue arrows point at the low impedance points. And then a quarter wavelength away is a high impedance point where the voltage is high in either positive or negative, and the current is low. And those are labeled with the red arrows. So if we feed the 40-meter antenna in the middle, we can use it on 15 meters. It's third harmonic, just like it was a half-wave dipole. It's not a half-wave dipole anymore, so the pattern is more complicated, but it's basically the same idea. I got this very nice and very complicated picture from ON4AA, and he did us the favor of plotting current along the antenna on all of the harmonics from the fundamental all the way up through the eighth harmonic. The even harmonics are above the dipole, which is that heavy line through the middle, this guy right here, and the odd harmonics starting with the fundamental. There is no first harmonic. There's only a fundamental and then second, third, fourth, fifth. So the even ones are above and the odd ones are below. All of the odd ones have a low impedance point in the middle. That's why you can use a half-wave dipole on its third harmonic, its fifth harmonic, its seventh harmonic, etc., and still have a reasonably good match to coax. You can feed it in the middle, and that's where the low impedance point is. But on the even harmonics, you have a high impedance point in the middle, and that's what makes the half-wave dipole hard to use on its second, fourth, sixth, eighth, etc. harmonics. But if you try to use your 40-meter dipole on 20 meters, you'll find that the SWR is quite high because it has a high impedance in the middle. So that's what's going on. You can see the distribution of current at all these different harmonics. You don't have to worry about that. There's no quiz on this. And I will make slides available to DARA. They're not copyrighted. You can distribute them, and everybody can enjoy the PDF format. So we look at these current waveforms along the antenna, and we see the low impedance for the odd harmonics at the bottom and the high impedance for the even harmonics at the top. Well, if we move along the antenna here, we can find a point right around in the middle of this ellipse here where the ratio of current to voltage is similar. It's not identical, but it's close. So if we were to figure out a way of applying power at that point, we'd have a similar impedance on multiple bands. And that is where the off-center fed dipole comes from. Points with similar impedance, and I've abbreviated this impedance of the off-center fed on multiple bands, you can find a point that has 100 to several hundred ohms of impedance on multiple bands. And so you use an impedance transformer to reduce the impedance to 50 ohms. Some of these things, the off-center fed dipoles, are fed with a 2-to-1 impedance transformer, or 4-to-1, or 6-to-1, and 9-to-1. These are all common, and that depends on where you pick your point along the antenna. You choose a feed point location so that SWR is in an acceptable range. It's not going to be 1-to-1, but it should be acceptable, something below 3-to-1 on multiple bands. You just have to find that tricky little point somewhere along the antenna. Here's a great graph. If you use a 29% offset, in other words, about 30% along the antenna, there's a point at which you can use a 4-to-1 transformer, and it will work typically on 80, 40, 20, 15, and 10 meters. That's a very common off-center fed dipole design. Now, I want to stress here that we haven't changed the wire at all. The wire is the very same wire that we drive as a half-wave dipole. The wire doesn't know that you're driving it off-center. It just knows it's a wire and it's got some electrons on it, and you've just picked a point along the wire that has an acceptable feed point impedance on multiple bands. You're just finding a sweet spot to do it. Other common designs are about a third of the way, 25% from the end and 20% from the end. Use different types of impedance transformers different ratios give you a different performance of the antenna. So you also have to remember when you put one of these things up that the feed point impedance will also vary with the antenna height, your ground conductivity, any other nearby antennas, whether the antenna is horizontal or whether it's sloping or whether it's an inverted feed. Those all affect the impedance at the feed point of the antenna. But if you fool around with it, technical term, you can find a spot along the antenna where you get an acceptable feed point impedance on several bands. That's the off-center fed antenna. Now, let's get to the heart of the matter. There is one other point along this piece of wire with similar impedance on all the bands, and that is the end of the antenna. All the bands you can see, whether it's an odd harmonic or an even harmonic, you get a high impedance at the end. The current is low and the impedance is high. So if we can figure out how to couple power to this antenna at the end, at the high impedance point, then we have a multiple band antenna. And I'm going to say it again, this is exactly the same piece of wire. It doesn't know any better. I know Mike Coulter is a great guitar player, and what I'm going to use an analogy here. Trying to feed something at the end is like trying to pick a guitar string right down by the bridge, where it has a very high acoustic or mechanical impedance. You have to pick really hard down there. You have to push really hard. You have to give it a lot of peak voltage to get current out of that string. And so all we're really doing here is looking at different ways to pick this guitar string. The center fed, you pick it right in the middle, you're going to get a lot of energy at the fundamental, and that wire is going to be moving back and forth. And as you move from the center out toward the end, you get less and less and less acoustic noise from picking the string, because the impedance is getting higher. Or you can also say it as you have to pick harder to get the same amount of sound out of the string. And out at the end, where the impedance is high, you have to pick real hard to get that high impedance point to supply power to the antenna. So the end-fed antenna, the off-center fed antenna, and the center-fed antenna, they're all the same antenna. They're exactly the same antenna. All that you're doing is moving the point along the antenna where you apply power. They have exactly the same radiation pattern, and they respond exactly the same to how you install them. Okay, so with that revelation behind us, the End-Fed Halfwave, at the end, typically, the impedance of the end-fed point ranges from about 1,000 to 5,000 ohms. That depends on the size of the wire, the height of the antenna above ground, the frequency at which you're using it, a bunch of stuff. But you can pretty much bet that you're going to wind up with an impedance somewhere between 1,000 and 5,000 ohms. High impedance points, it's important to remember, are affected by capacitance. It doesn't take very many picofarads, even at HF on the low bands, to drag that impedance down. You may have 5,000 ohms, and then you have the antenna close to something metal, and that capacitance there between the antenna and the something metal will present enough reactance to lower that impedance. So all these different things affect the high impedance at the end of the antenna. You have to remember that. And it's actually quite hard to get an impedance of 5,000 ohms or more because of this capacitance. Any little thing will shunt the current around your impedance point. So you have to work really hard to get that much impedance. So somewhere between 1,000 and 5,000 ohms. How do we deal with that? Well, the first problem you're going to have to deal with is for any amount of power, you're going to have high voltage at the feed point. If you're feeding a dipole at the middle where the impedance is low, you're going to have a lot of current, but not such high voltage. But boy, out at the end, you can really get some high voltage. As a matter of fact, at the end of an antenna, any antenna, whether it's a whip or a dipole or something else, it's enough to actually cause an RF burn. And if you're not careful when you're driving around with your mobile and you park under or in a tree, you can set the tree on fire. Don't ask me how I know this. And I found that out the hard way. So you got to watch out. There's high voltage at the feed point because you're at a high impedance point. You're picking that guitar string really hard. Okay. And the other difficulty is you get a lot of capacitive coupling to just about everything. Your feed point, the ground, your car, whatever happens to be handy, you've got to remember that it doesn't take much capacitance to affect your feed point impedance. Here are some other End-Fed half-wave antennas. Over at the left is the original End-Fed ZEP. You may have heard the term End-Fed ZEP or ZEP antenna. That comes from Zeppelin, which was the original term for those big gas-filled airships. And the radio operators in those things, they would just dangle a wire out of one end of the radio shack and let it trail down below the airship. And if it was a half wavelength long and they used quarter wavelength feeders, it presented an acceptable impedance to the transmitter. And that was called an End-Fed ZEP. That's where that comes from. Remember, it's got a funny name, but it's just a half-wave dipole fed at the end. In the middle, down here, is a half-square antenna. And what it is a wavelength of wire with a quarter wave vertical, half-wave horizontal, another quarter wave vertical. And you wind up with two vertical elements with current doing the same thing either way. And so this acts like a pair of verticals, and you get a broadside pattern out of the half square. And then in the middle is the bobtail, and it's almost like a half square with another half of the square on the end. And here's a technique for feeding these things. You put a parallel LC circuit together, you turn it to resonance, so it's resonant at the frequency you're trying to apply power, and then you very carefully attach the coax along that coil until you find a 50 ohm point, usually down at the bottom. And you have to be real careful when you're doing this because you get a real nice RF burn. Don't ask me how I know that either. But the bobtail is like three vertical elements in an array. And then over at the right is the bi-square, which is a pair of half-wave dipoles stretched out into a diamond. It looks like a loop, but it's not. Each antenna, they go from the top, they're separate, they go out, and then down. And so they're a pair of End-Fed dipoles on one support. And that works pretty well, too. A lot of soda operators will take a fishing pole and a couple of pieces of wire and use a bi-square up there on top of the mountain. Okay, so let's review. Three identical antennas, the half-wave dipole, the off-center fed dipole, and the End-Fed half-wave are the same antenna. You're just applying power at a different point to the same antenna. And the reason you would pick one or the other is for reasons of convenience. If you like using the center fed with coax feed at the center because you get a nice UR, good. If you want to use it on multiple bands, and so you find a feed point that's about a third of the way out and use an impedance transformer, that works too. And then also at the end, if you've got the right impedance transformer, you can use it on a whole bunch of different bands. But there's no difference in gain, and there's no difference in radiation pattern. They're all the same antenna. But they have bugs and features, and so it's an antenna system choice that you're making. You have to deal with transformers, the weight of a transformer. There's a little loss in the transformer. What about feed line loss? If you have a high SWR, say for your off-center fed antenna, you've got to deal with loss in the coax. What about the number of supports? If you're going out for a portable operation, you may only have one support. Or if you can get it up in trees, maybe you can put it up there horizontally. And then there's the weight factor. If you're climbing a mountain with this thing, you've got to really keep the weight down, and that includes the supports too. So after you balance all these different things, fixed station, portable station, ultralight station, then you come up with an acceptable set of the requirements. There's the R word for engineers, the requirements for your particular operation, and that's how you pick the halfway, the center, off-center fed, or the end-fed. So we picked an end-fed antenna. How do we feed this? Okay, the key to a good end-fed half-wave design is that transformer. And before there was a really solid transformer design, end-feds were reported to have all kinds of problems. They were difficult to apply power to. They had weird SWRs. They were very sensitive to any kind of installation weirdness. And so they got kind of a bad reputation. And then all of a sudden, somebody, K1RF is the somebody, really took this thing apart. AA5 LF, I think, is the other guy. And the two of them solved this problem and said, okay, here's how to do it. Well, so you've got to pick the right impedance ratio for that transformer. What is the right impedance transformer? Well, remember that we're varying between 1,000 on the low end and 5,000 on the high end. Okay, well, geometric mean is the way to figure out what's electrically halfway in between those. Engineers love geometric means. You multiply the two numbers together at each end of your range, you take the square root. That's the geometric mean. Well, 1,000, 5,000 ohms, the geometric mean is 2,236 ohms. So your optimum ratio for the impedance transformer would be 2,236 divided by 50, or an impedance ratio of 45:1. Okay, so in a customary transformer, the impedance ratio is the turns ratio squared. Well, you don't get an integer that comes up when you square it to get 45, but how about 49? That's pretty close. You've got 7 squared. So a turns ratio of 7 will give you an impedance ratio of 49. Well, what's the result from that? Well, if you have 1,000 ohms and you divide it by 49, you get 20.4 ohms, and that's a 2.45:1 SWR. If it's right in the middle of the range, 2,500 ohms, you wind up with 1.02:1, which is pretty good. And if you're at the high end, 5,000 divided by 49 is 102 ohms, and that's 2.04:1. So across our entire range of expected end-fed impedances, we can apply a 49:1 impedance transformer and get SWR that varies between about 1 and 2.5, and that's pretty good. Here's how to build that transformer. This is from Steve Dick, K1RF. Isn't that a cool call? K1RF, this is his design. For a 49:1 transformer, the primary has 2 turns that are tightly coupled to a 14-turn secondary. And if you go and look up his presentation, he will go into great detail about how to do this. So you use a toroid ferrite core type 43. You have to use the right mix. If you use a type 31, you won't be happy because it will act as a lossy core. If you use anything like a 61 or 75 or all these different options, they won't behave the way that you expect them to across the HF bands. Use a type 43. Type 43 ferrite is the same stuff that you see in those little molded on lumps on your monitor cable and stuff like that. Above the HF bands, once you start getting up above 50 megahertz, type 43 starts acting like a lossy material. And that's good because it's trying to soak up and get rid of RF flowing out of a computer or something on a cable. But below 50 megahertz, it acts like a very not lossy and inductive material. So it's good for passing power through and making transformers out of. So you have 2 primary turns, 14 secondary turns. There's a little tiny capacitor down there at the bottom. You can see it. Some designs use picofarad, 300 or 390 picofarad. What that does is those windings start to act like inductors. As you get higher and higher in frequency, you get a lot of inductive reactance, and that would upset the performance of the transformer for your purposes, which is to make it basically a flat impedance all the way up to 10 meters. So this capacitor sort of cancels out that inductive reactance of the transformer and makes it work on all of the HF bands. You'll note also that the primary turns are twisted with the secondary. Basically, the wires are just twisted together, and that makes sure that the energy is coupled really strongly from the primary to secondary. If you build one of these things, you have to use insulated wire. Most designs use enameled wire. Make sure you don't nick it or scratch it so that it can short either to the ferrite or to the other wires. You can use plastic insulated wire as well. All right, now we've got an issue. On the right, you can see one of these transformers. You can see the little tiny coupling capacitor down there at the bottom, the little orange thing. You can see the windings of the transformer. Now we look at the schematic over at the left. Well, on the input side, we connect our coax directly across the primary winding, no problem. In on one terminal, out on the other. But what happens on the secondary side? You've got this nice big 14-turn winding, and one end is connected to the antenna. Well, where is the current going to flow out of the other terminal? How does the current form a complete circuit there? So we're missing a current path, and where is it? Okay. W7EL, Roy Llewellyn, is the guy that designed EasyNet, and he's written a number of really good things in the antenna book and articles in QST. And he said, okay, where's the current? Let's build one of these things, a really good model of this thing, and I'm going to feed it with open wire line, which you can see over here. That's this stuff. And this is the antenna over here. All right, where is the current in all these things? And here, this red line is the antenna current. All right. And he discovered that there are not equal currents in each side of that feed line. He found that there was a little bit of difference right here between the current in each side of the feed line. And that's called common mode current. And it's abbreviated here, I for current, CM for common mode. And that's where the missing current is. It's flowing on the feed line. In coax, it's flowing on the outside of the coax shield, which is electrically different. It's completely distinct from the inside surfaces of the shield in the center conductor. Okay, so, well, what are we going to do with an End-Fed antenna? Obviously, we're not going to put it up like this. Well, we can supply a ground screen underneath so that the current can flow through the ground screen and back to the secondary of the transformer. We can use the shield of the coax. We can put on a counterpoise wire. We can even connect the antenna directly to the earth. All these things supply a current path back to the transformer, and that's why in most designs you see this point, the bottom, the cold end of the secondary connected to the ground or shield side of the primary. This is the missing current path. The antenna radiates high common mode flows on the outside of the coax back through this connection to the secondary of the transformer. That's how you feed the end of this antenna. Okay, let's talk about counterpoise. A lot of things are called a counterpoise. Wires, screens, radials, all this kind of stuff. What's the point of a counterpoise? It's a very old word. If you go back into the 20s and the teens, you'll see counterpoise. A true counterpoise is only there to couple the antenna to the earth. It supplies a missing connection. And if you look at the old days when the word was invented, it's basically, it looks like a big capacity hat, and that's exactly what it is, but it's at the bottom of the antenna, and it acts as a capacitor to the earth. But the word is used for lots of different things. The whole point of when we talk about counterpoise to the End-Fed Halfwave is for it to lower the impedance, lower and stabilize the impedance at the attachment points. So it's not so crazily affected by the ground and by nearby conductors and all sorts of stuff. It just basically couples the antenna to the ground and stabilizes that feed point impedance. So what do we use for an End-Fed half-wave counterpoise? Well, there are a number of schemes. The easiest by far is to simply allow the antenna to couple to the outside of your coax, and that's the counterpoise. That's the missing part of the antenna. Effectively, the current flows from the antenna through the air back to the outside of the coax and back to the transformer. That's the circuit. So that's the easiest thing. I have an End-Fed half-wave at home, and the feed point is about 4 feet above ground, and the antenna goes up a flexible pole and then up into a tree, and the coax just lays on the ground. That's fine. That works just great. You can also use a ground rod if you want. It's not necessary, but you could do that. The problem with using a ground rod is that makes the current flow through the dirt. And what is the resistance of dirt? It's pretty high. It's 10 ohms, 20 ohms, 50 ohms. It's lossy. So if you make current flow through the dirt, you're going to be heating up the worms and not the ionosphere. So that's generally not a good idea. You can also lay out a piece of wire, a counterpoise wire. And all it really is more of the antenna. You're just creating another 5 to 10 feet of antenna and laying it on the ground. That's what the counterpoise is. It's much easier to use the shield of the coax feed line. Now, say you're operating from a picnic table and the End-Fed half-wave impedance transformer is very close by, and you don't want to get too much RF into your, maybe it's a laptop, or you don't want to upset your radio keying or a keyboard or something like that. Or maybe you've got an RF burn on a hotspot. Okay, well, so you put a choke balun right at the impedance transformer. You either wind up some of the cable or use a ferrite choke to block current flowing on the outside of your coax. Well, you also just block your current path back to the transformer. So if you're going to put a choke on the feed line, you have to replace that current path with something. The easiest thing is just to throw out about a 20th of a wavelength at the lowest frequency of operation. That's about a 5 to 10 foot piece of wire, and connect that to the ground terminal of the impedance transformer and throw it on the ground. And then don't step on the end, which is going to be at high voltage. Don't ask me how I know that either. You're going to have high voltage at the far end of the antenna and at the end of your counterpoise. You can install these things with the feed point. Generally, most people install them for portable and summits on the air operation with the feed point low, a couple of 3-4 feet above ground, and then they run that wire to whatever support they've got, whether it's a tree or a pole or what have you. You can also put it up in an inverted V fashion, so it goes up from the transformer, and then there's a support, and then it comes down on the other side. You can also put these things up, typically a fixed station, you'll put it up in a horizontal, like it was a dipole. Hey, it is a dipole, okay? So you've got the transformer at one end, and then you run the wire out to some kind of a support. Now, that end is going to be feeding the outside surface of your coax, so that's going to become part of the antenna, and you might need to tune or trim the antenna to get the exact frequency of minimum SWR that you want. You also have to be aware when you're operating portable or summits or anything else in a park or any kind of public space, a lot of places do not allow you to drive anything into the ground, not so much as a tent peg. So you will not be able to use the ground rod method, and they really don't like you throwing stuff up in trees either. So what might work the best is to get one of those multi-section fiberglass poles and hold the antenna all the way up as far as you can get it. You can start with the transformer at the bottom, run the wire up the pole, and then just slope it down someplace to where you can conveniently tie it off. Remember, that's a high voltage point, and make sure that people can't accidentally walk up and go, hey, what's this? Ow! So you don't want to have to explain RF burns to other park visitors or particularly a park ranger. So you just have to be cautious about where you're putting your antenna, just like any other antenna. Let's go back to why 49 to 1. End-Fed available, or End-Fed halfwave antennas are commercially available with everything from 9 to 1 to 81 to 1 transformers. That's a turns ratio of 3, 4, 5, 6, 7, 8, or 9. How do you choose? It depends on how you're going to install the antenna and how long it's going to be, what bands you're going to use it on. Remember that the impedance varies over quite a wide range, as we talked about before. That impedance is going to change with frequency. It's affected by ground and height, and anything nearby that conducts, like a pole barn with steel building materials, or your car, or swing sets, or fences, all sorts of things. Okay, so if you look at the graph on the right, what I've done is plot SWR over the range of 1,000 to 5,000 ohms at the antenna for different turns ratios. You can see, starting with the light blue curve, that it starts at a reasonably good value of SWR. The numbers are a little hard to see. Down at the bottom is 0, and then 1 to 1 is that first section right here. So a little over to 1 to 1 at 1,000 ohms, but that 9 to 1 transformer, your SWR goes up quickly as the impedance of the antenna increases. And so as I change the impedance ratio from 9 to 1 to 16 to 1 to 25 to 1, so on and so forth, you can see that the SWR curve flattens out a little bit. And then as I go all the way up to 64 and 81 to 1, then it starts to get high at the low impedance and flattens out at the top. The compromise one, the one we really want, is this guy right here, this light blue curve right there. And that's our 49 to 1 that goes from 2.45 to 1 at 1,000 ohms to 2.02 to 1 at 5,000 ohms, with a nice big flat range in the middle. And that's why 49 to 1 is so popular. If you're going to build one of these things, I suggest you start with a 49 to 1 impedance transformer, and then feel free to experiment if you want to. Okay, so why is this thing so popular? We've had dipoles forever. We've had off-center fed dipoles forever. And all of a sudden, End-Fed Halfwave. Wow, these things are fantastic. What's the deal? Well, for one thing, it's useful. It's really efficient. Dipoles like to work. They're not complicated. The current flows back and forth along them, and that's what makes an antenna radiate, is electrons flowing back and forth in a straight line. That's what makes an electromagnetic field, and it radiates a signal. It's called ampere feet. The number of amperes times the number of feet over which that amperage flows. If you can get current flow in a straight line in an antenna, it will radiate. But the End-Fed Halfwave also has some mechanical features. It's light, and it only requires the one support. A lot of people use it that way. There's a 160 to 10 meter version. That's 260 feet long. That's a half wave at 160 meters. That's a little longer than most yards and parking lots and picnic grounds, things like that. The 80 to 10 meter version is 132 feet long. That fits in a lot of backyards, and it's not too big for parks and other public spaces. I found that if you cut the antenna halfway along it, and if you put in a series capacitor of about 470 ohms or something, 470 picofarads, you can cause the 80 meter resonance to move up the band into 75 meter phone area. So you can use this for MCOM and 75 meter voice operation. It doesn't affect the higher bands very much at all. And if you want to, you can make a little jumper with the capacitor and then lower it, take the capacitor off, put a little jumper of wire around your insulator, and you're back to the basic configuration. You can also use this as a quarter wave ground plane on 160 meters. Basically, you take away the impedance transformer. I just disconnect the wire, the antenna wire from the terminal, and I drive it directly with coax against some kind of a ground screen. I just use rolls of chicken wire. So I can put those out. Say I want to go out and do the 160 meter contest. I'll just go ahead and disconnect the impedance transformer, and then I connect my coax directly between the ground screen and the antenna. I found that in my particular instance, all it took was a 2,000 picofarad series capacitor, and I had a really nice one-to-one SWR. That capacitor was a World War II vintage mica capacitor, and one of those sealed things that you see in your junk box. And I'd had it for all these many years. It was just waiting, and here I put it to work in my backyard, feeding my 160 meter wire. It's really an 80 to 10 End-Fed Halfwave, and I made it into 160 meter vertical. So you can do that. There's also a 40 to 10 meter version, about 67 feet. That's very popular for portable operation. And some designs, you can add a loading coil at the end of the antenna for 80, and that gives you a narrow slice of 80 meters. And you can also experiment by clipping on resonator sections and get 60 meters. And you can optimize this for 17 and 12 and all sorts of things. It's just a dipole. It's just a piece of wire. So feel free to experiment with this stuff. You want to make your own? Download and study the K1RF presentation. Just enter search term, which is K1RF End-Fed Halfwave, and you will find it. Be prepared to adjust the length of the antenna based on your circumstances. And you'll see some designs that have a 6-turn loading coil near the feed point. It's about a microhenry and a half. And what that does is it lowers the resonant point on the higher bands. Those of us that use the 40 meter dipole on 15 meters notice that the point of minimum SWR on 15 meters was not exactly 3 times the point of minimum SWR on 40. And that's because the antenna doesn't have ends at each end of those 3 dipole sections that we saw earlier in the presentation. So what you would do is add a little capacity hat about quarter wavelength out on the higher bands. And that's what the function is of this 6-turn loading coil. It's about a microhenry and a half, about an inch and a quarter, 6 turns on a little piece of PVC. That's what that's for. If you're going to build your own impedance transformer, make sure you use mix 43, type 43. For QRP, you can use a small 1-inch core, 1-inch diameter core. If you get to 100 watts, use a larger core. 1.4 inch is the minimum. And if you're going to start using FT8, which is 100% duty cycle, or you're going to run higher power, use at least 2 cores. The full power impedance transformers use 3 cores stacked up as if they were one. And to keep these cores together, you wrap them with a good quality electrical tape like Scotch 33 or 88. Remember to use enameled wire, not bare. The primary and the secondary are coupled magnetically, but they must not connect to each other galvanically, in other words, directly. And the compensating cap that you use, typically 150 to 100 picofarads work pretty well. Get one of the high voltage 3 kilovolt units. They're not expensive, but those are the ceramic capacitors, and they're rated for low loss, so you can use them for transmitting. Watch out for high voltage at the feed point. I'll reiterate that. If you put these things down so that the transformer is at about 4 feet above the ground, any inquisitive person can walk over and touch it. So just make sure you keep that high voltage point away from people. You can install it, as we saw, as a sloping antenna with a center point, or even horizontal. And if you do have RF in your station, in your shack there at the picnic table and a portable, and you don't have a fancy ferrite choke with you, just wind up some of the coax 6 to 8 turns, about 6 to 8 inches in diameter. There are a number of these designs in the antenna book, and that will put enough inductance in the outside surface of the line to help reduce common mode current. And use good quality coaxial cable. If you're weight limited, if you're hauling this thing to the top of Mount Pisgah or whatever, use RG174 or lightweight Teflon cable. But RG174 is quite lossy even at HF. Use 25 feet or less of it. You're hauling all your stuff all the way up to this mountaintop. Don't waste your power by using a long run of lossy coax. RG58 is great for 100 watts to about 100 feet. But be careful, there's a lot of real junky RG58 type cable. All these RG numbers are no longer mil-spec numbers, so anybody can call anything RG whatever, and they're not violating any rules. If you want to check, strip away some jacket. The braid should be nice and shiny, and you should not be able to see the center insulation through the braid. If you see gaps in the braid, it's not really good quality cable. RG8X or RG213 will work for QRO and for longer runs than 100 feet. So, in summary, it's the End-Fed Halfwave. It's a half-wave dipole on its fundamental, but it's just fed at one end. You're just picking the guitar string at one end, not in the middle. So it's fundamentally the same antenna as a half-wave center-fed dipole. You just change the feed point. And the off-center fed dipole is the same as well. You're just applying power at a different point because it's electrically convenient. These things operate on multiple bands because they have a at the end, which sort of solves the variable impedance problem. But it requires a well-designed and constructed impedance transformer. That's the secret sauce for the End-Fed Halfwave. And then you've got to balance your other trade-offs, mechanical, weight, supports, et cetera, with the other dipole type antennas. And so that is my story on the End-Fed Halfwave antenna, and I would be delighted to take some questions. So I'll let somebody from DARA run up to the front of the room and translate the question for me. There he is now.
Do we have questions? He has answers.
Maybe I just baffled him.
Do you have any online questions there, Logan?
Where can I get this presentation?
Well, the question was, where can we get this presentation? Well, I'm assuming you're going to send it to me or someone, and we'll get it out on the site.
I will reply to your email asking where the heck am I, and I will include these slides. I apologize for getting wrapped up in my project. I know nobody ever gets wrapped up in projects, and then suddenly I get this call from Mike Halter. I go, uh-oh. So anyway, yes, I will send the slides.
Yeah, you may have sent them to me already, but if you'll do that, that'll be good.
Okay.
What's the difference? What's the difference between this and a random length wire End-Fed?
And a random length. Okay. Well, the End-Fed is resonant. You design it to be resonant on its fundamental band. The random wire is random, could be anything. You will find a widely variable End-Fed impedance, and you use a tuner, and maybe you can match it to 50 ohms, and maybe you can't. Sometimes the random wire looks like an End-Fed half-wave if it's resonant on the frequency of use. But other than that, there's no fundamental difference except that the End-Fed half-wave is a half-wave resonant dipole on its fundamental frequency.
Okay, we have another question there.
Any guidelines on feeding an End-Fed, let's say 20 feet above the ground, the gutter is right there, and the gutter pipe is right there at the feed point also, and the gutter pipe's about 15 to 20 feet. Are there any rules of thumb in creating a distance between the feed point and the aluminum gutter system?
Okay, that's a good question. So you're going to put the impedance transformer up at the roof line, and that's where the gutters are. Okay. Well, first of all, don't run the coax or the antenna parallel to the gutters, if at all possible, because they will couple very strongly. They're electrically very close, and it's hard to predict what the effect will be. If you are orienting them perpendicular to the gutters, that's a much better situation. Okay, so the coax is going to hang down from the impedance transformer, probably below the gutters. Because it's above ground, about 20 feet above ground, that 20 feet of coax shield is going to be part of your antenna. And you will have to adjust the length of the antenna, probably at the far end. That's the easiest thing, until you get the resonant frequencies where you want them, because you've got 20 extra feet of antenna. And you can also control how much of the coax you're using as counterpoise by placing a choke, either a coil of coax or a ferrite choke, maybe 5 to 10 feet away from the feed point, and that will also sort of work. But with it up in the air like that, you will, and close to a conductor, you will have to experiment with the tuning of the antenna. So make it easy to lower the far end, I guess.
And use a fiberglass pole instead of a metal pole, right?
Question again, what?
I said use a fiberglass pole instead of a metal pole.
Yes, if you're running the antenna up the pole, don't use a metal pole. Use fiberglass or PVC or wood that doesn't conduct. Otherwise, the part of the antenna that runs along the pole will couple to the metal, and who knows what you're going to get. And I guess I'll bring out another point is if you want this thing to radiate effectively, you want to get the points with the highest current where the antenna is radiating from as far above ground as you can. On the fundamental, that high current point is in the middle, just like a regular dipole. As you get higher and higher and higher in frequency, the high current points move around on the antenna. So if you've got a band that you really care about, say 20 meters, you want to work some DX on it, try to get the high current points on 20 meters up and away from ground. Whether you do that with a support on each end or a support in the middle or whatever, the higher it is, the better it will play. Also, a horizontal polarized antenna at low heights will probably perform better than a vertical one. So if you can get the maximum amount horizontal or sloping, you'll probably get better results than with a vertical. The reason that is because the vertical field causes current flow in the earth, and that's lossy. So you avoid it with horizontal polarization.
A question about trees. When I camp or I go out in the country, how far away from the trunk of a tree should I be concerned about mounting that transformer?
Oh, I would say a foot or so would be fine. There were some studies done. There's some QST articles by Ty Siwiak, KE4PT, on coupling between antennas and trees, but you're not talking about running the antenna directly along the tree. You're talking about putting the impedance transformer, supporting it from a tree, and then running the coax down the tree. You won't have much coupling. So a foot or two should be just fine.
The question is about carbon fiber poles. Are they acceptable?
You mean carbon fiber pole?
Yeah, rather than fiberglass, a carbon fiber.
Yeah, carbon fiber. Well, I'm famous for answering all questions with it depends. It depends on how the fibers are. I guess I wouldn't say supported, but the fibers are mixed with a resin that is the fibers are embedded in this stuff, and they give the overall pole strength, but they're probably not conductive. If you scratch off a little of the coating of your carbon fiber pole and put a voltmeter at each end of it, you shouldn't see you should see a very high resistance, I'll put it that way. If you see a low resistance, it would not be suitable. But I think most of the carbon fiber poles are non-conductive to various degrees, and those would be okay. But if the carbon fiber pole is conductive, don't use that.
Ward, you did an excellent job selling the End-Fed Halfwave to me. I guess my question for you is, what are some of the disadvantages of it compared to other antennas?
Well, it's a long wire, okay, and it's really hard to use as a beam. You're not going to be able to turn it around and that kind of thing. Typically, some people find it difficult to use because of their particular circumstances, like the fellow with the gutters. it just might not work for you because of where you have to install it, and that's generally the problem. So it's no worse than an off-center fed dipole or a center-fed half-wave dipole. It offers several advantages, which are the low SWR on several harmonically related bands. It makes it easier to use than center-fed antenna with open wire and a tuner, for example. That's very popular, and it has been for many years. But you have to worry about feed line loss, and you have the expense of a tuner. So if it fits your circumstances, easy to use for parks on the air and summits on the air and stuff like that, and that's very popular. I'd say give it a try.
Ward, I got a question. On QRO, if you're going to run full legal limit, you said 3 cores stacked would probably do the trick. On the enamel wire, is there a certain gauge that you would recommend? Do you want bigger wires or you want smaller? Because you're trying to dissipate that heat as fast as possible.
Right. Well, if it burns up, it's not big enough. How's that? Typically, at the 100-watt level or bigger, number 14 is just fine. I don't think anybody has to use, number 12, number 10. Boy, that's hard to wind on those little cores. Down at the QRP level, you could use number 18, number 20. You don't want to get so small that you start to get resistive losses in the wire. You're going to all the trouble of putting this thing up in the air and everything. Don't burn up your watts in the wire. Number 14 is kind of the standard go-to, and it's available inexpensively and with really good enameled installation.
So that 14 will work for 1.5K?
Okay. Well, are we done?
Is there such a thing as an End-Fed fan?
Oh, okay. Anything you can do with a regular dipole, a center-fed dipole, you can also do with an End-Fed. Yeah, you could put up 2 or 3 different End-Feds and feed them at the end, but you don't have to do that because they all have the same impedance. The reason you do a fan center-fed dipole is to create that low impedance point on all the different bands. And so you've got to have the 2 pieces on each band. You have the lowest with the longest, and then they get shorter and shorter and shorter. But with an End-Fed, it does that automatically because of the harmonic relationship of the currents along the antenna. So you could, but you don't have to.
Do you have an opinion on using a transformer versus an auto transformer?
People have done both. I think the problem with the auto transformer version is it tends to not, the impedance ratio tends to change a little bit toward the higher frequencies. But people have used the auto transformer, and they've also used the primary secondary version as well.
Thanks. What about putting a choke at 20 foot near the group? Is a counterpose required if the group should be ground?
Let's see. Well, the counterpoise, if you're 20 feet above the ground and you're running coax up there, that 20 feet of cable is your counterpoise, the outside surface of the cable. You don't need an extra wire. What I would do is I would just go ahead and use it, trim the antenna until I get the resonant frequencies that I want, and then put a choke where it either comes into the house or gets down to ground level. And then electrically stabilize the design that way.
Ward, I think that's about it. So thank you very much for a great presentation, like always. And does your antennas always do spurious emissions?
Well, you know, we keep talking about it. One of these years, I keep telling everybody, well, the band's in rehab, so you know, when we get out of rehab and get our blood changed and all that kind of stuff, you never know. So we'll let you know as soon as we do. Thanks for your interest. I appreciate it.
I just couldn't resist that one.
There you go.
Thank you, Ward.
All right. Well, again, I apologize for being late and getting everybody upset, but here we are, and I will see you guys at the Hamvention. Thank you very much for putting on the show for us all.
You're welcome, Ward. Thank you.
73.
7-3, Ward.